Hello, students. Today we are going to discuss the concept of rotational inertia. Rotational inertia. First of all, I would like you to think about this situation. We have a rod, and this rod is spinning, or we'd like to spin it through a certain axis. This is the axis of rotation, and we spin it like that. This is the axis of rotation. Let me point it. It's one. This axis of rotation. Axis of rotation, and that's the rod. So this is a rod, and you'd like to spin it through this axis of rotation. You can also have a situation whereby you have the rod, maybe this direction. So you can have your rod downward, and then you spin it through this axis. You do the same spinning like this. Now, as you can see, if the rods here are spinned through different axes of rotation, with one at the end of the rod, one is an axis throughout the body of the rod, we are going to have different experiences in terms of spinning the two. So as you can see here, the first one, it will be harder to start rotating. So harder to start rotating. Still be harder because, I'm comparing with the this one. This will be easier. So this will be easier to start rotating. Easier to start rotating. We also see something interesting for this case. This is the first rod. It is harder to stop rotating. So it is harder to stop rotating. Once it gets spinning, it is harder to stop rotating. If it was rotating, it's harder. Now we have to compare that to this one. This one is also actually easier to stop rotating. Easier to stop rotating. Okay, so looks like it's something interesting here. If most of the mass of the rod is away from the axis of rotation here, we see that it is harder to start spinning or rotating, but also it is harder to stop spinning. These are the observations. Whereas if the axis of rotation is through the rod, in other ways, most of the mass of the rod is within the axis or is close to the axis of rotation, we see that it's easier to start rotating or to rotate this, but also it is easier to stop spinning or to terminate the spinning. So here we have this concept, what we call rotational inertia. So we can say that the rod in the first situation has more rotational inertia compared to the rod in the second case. So if this is rod A and this one is situation B, so we can say that the rod as shown in example A has more rotational inertia compared to B. So A has more rotational inertia compared to B, compared to case B. So this is a conclusion, and we have to understand now what is rotational inertia. what is rotational inertia? What is it that causes situation A to have more rotational inertia and not or situation B? All right, so rotational inertia is just the tendency of an object to resist changes in rotation. The tendency of an object or rotating object to resist changes in rotations. It is a similar concept to inertia when we talk about linear or translational motion. It is a very similar concept. So rod A, when we say it has more rotational inertia, what we are trying to say that it has a tendency to resist rotations. That's why it's harder to start rotating, and also it is harder to stop rotating compared to case B, right? All right, let's look at another example, and then we can understand better the concept of rotational inertia. The other example is the case whereby we have something orbiting around a circle. Have a center here, and that's our object here. If you compare this case and compare with the larger circular path, center here, this is the radius of curvature. This is the radius here. The masses are the same here. I'm using the same masses, same mass, but radius is larger in case number 2. So this is 1, this is 2. Because of that, we are going to see that in terms of axis of rotation, we are going to see that case number 2, the mass will have a larger rotational inertia. So case 2, we have a larger rotational inertia. Case 2, larger rotational inertia of the mass. Rotational inertia of the mass. So in this case, we see that the mass is actually distributed away from the rotational axis. In this case, this is the axis of rotation. In this case here, that's the axis of rotation here. So when the mass is distributed away from the rotational axis, we usually have increased rotational inertia. When the mass is close to the rotational axis, we have reduced rotational inertia. And that's why it is actually easy to spin a ball when the string is actually shorter. When the string is longer, like in this case, if you try to spin a ball on top of your head, it's usually harder. It's harder to get the ball started. And also it's harder to stop the ball from spinning on top of your head. It's because of an increased rotational inertia. Recall that rotational inertia is the tendency of a rotating object or a tendency of an object to resist changes in rotation. That's the concept of rotational inertia. Now, as you can see here, we might maybe think about now, what is the rotational inertia in different cases or for different objects. So here I have the results of rotational inertia for different objects. Rotational inertia. Rotational inertia for different objects, of selected objects, I should say. All right, so for example, simple pendulum. If you have a simple pendulum, maybe think about displacing something here like a ball. And we have this as our radius here. This is the mass here. In this case, rotational inertia, which has a symbol I, is just equal to m times radius squared. That is the simple case of a simple pendulum. If we have a solid cylinder, maybe think about solid cylinder like this one, and then the axis of rotation is here. Rotational inertia here is given as I, which is the symbol for rotational inertia, is m, actually r squared, and then there's a half over 2, yeah, half m r squared. And for a sphere, we have a sphere like here, it's a sphere. By the way, it's a solid cylinder, so we have to solid cylinder. And this one is the simple pendulum. Simple pendulum. All right, solid cylinder, and then this is what we call a sphere of radius r, and the axis of rotation is through the center here. This one has rotational inertia of 2/5, mass of the sphere times radius squared. As you can see, rotational inertia depends on the mass distribution as well as the axis of rotation, as you can see. So we have also a case of a hoop. So if you have a hoop, well, this one is a sphere, remember? This was a sphere. If we have a hoop, how can you draw a hoop? So a hoop usually can draw a hoop like this. That's the hoop. Okay, so if it's a hoop, trying to draw a hoop here. For a hoop, we see that about the center, I mean, if the axis is through the center, this is the radius of the hoop, rotational inertia will be given by m r squared equal to m r squared. Now remember, for a solid cylinder, it was m r squared over 2, but for a hoop, it's m r squared. A hoop has most of its mass at position r. So it has no mass on the center, but most of the mass is somewhere around position r. And the rotational inertia is that one. All right, so different objects have different rotational inertia. Let's see if we can add more. Well, you can find more of these if you check from in your textbook. You'll see that different objects have different formula or expressions for rotational inertia. Now, I would like you to take note of the hoop and the solid cylinder because these are very interesting cases. So notice that, I'd like you to notice that a hoop has greater rotational inertia, relative to its own mass, So that is very, very important. So a hoop in general has a greater rotational inertia relative to its own mass. This is not clear. Relative to its own mass. So the fact that most of the mass of the hoop is distributed away from the axis of rotation, we see that a hoop in general has rotational inertia that is larger. Now, remember, when most of the mass is distributed away from the axis of rotation, rotational inertia is larger. Now, if we do an experiment to see which one wins the race down an inclined plane, we see that the hoop will always lag behind the solid cylinder. So if I have the hoop here, yes, that's the hoop right here, and the solid cylinder will be winning the race because of having the smaller rotational inertia. Okay, so that's the solid cylinder. This is the direction travel, that's velocity v, and this one the direction of travel, velocity is v. So we see that the solid cylinder is actually easy to rotate because of the small inertia, so easy to rotate, wins the race. So it wins the race. And this one here, it's actually lazy to rotate. Lazy to rotate. Or now remember, is rotational inertia is equal to 1/2. Sorry, this one is mr squared. Mr squared, and the rotational inertia for this one, rotational inertia was 1/2 mr squared. And as you can see, this one has less rotational inertia compared to this one, and therefore, if you have less rotational inertia, that means you can easily spin. This can easily spin. You can easily get it started, or you can easily stop it. I mean, it wins the race. It spins faster compared to the hoop right there. So on an inclined plane, that's why the solid cylinder will win the race. The solid cylinder. And this one is a hoop. That's the hoop there. Now you might protest. You'd say, well, maybe depends on the mass. Well, you might say maybe if the solid cylinder has more mass than the hoop, it will be different case. That can be an argument that you can make. But I would like to remind you a few things about falling objects. I'd like to remind you a few things about falling objects. So I would say that results above are valid. Okay, so let's write this one. So results are valid even when the mass of the hoop is different. Even when the mass of the hoop is different. Is different from what? From mass of the solid cylinder. Now, I want you to recall that different masses, different masses fall at the same rate. Fall at the same rate. I hope you remember this. Fall at the same rate under the influence of gravity only. Or I should say in free fall. In free fall. So in free fall, we see that different masses fall at the same rate in free fall. And likewise, if the masses are placed on an inclined plane, different masses will slide at the same rate. Recall also that even if we have let's say we have 2 blocks of ice here, 2 blocks of ice. I don't know how to draw them side by side, but there are 2 blocks of ice here, 2 blocks of ice. Let me just put one here and then another one in a different place. So a block of ice there, and then let's have another slope. Let's have another slope here. Okay, so the slopes have the same height, and then we put another block of ice here. Now, this has smaller mass and this one has a larger mass. This block of ice, which actually moves down, where we can ignore surface friction, we see that mass doesn't matter here in terms of how fast they fall to the ground. So if you do this experiment, different masses, a small mass and a bigger mass here, will actually arrive at the bottom at the same time, as long as this is a frictionless, as long as this is frictionless. So the point is, we see that in free fall, objects fall at the same rate. In other words, if you drop two objects of different masses from the same height, they will touch the ground at the same time. Likewise, on an inclined plane, mass is not an issue. Different masses will speed up at the same rate and they will touch the ground at the same time. So for that reason, in this experiment, whereby we see that the hoop actually loses the race with the solid cylinder, our explanation should focus on how the rotational inertia formula looks like. We shouldn't worry about the mass, because mass doesn't affect the way things fall down to the ground in free fall or the way objects fall down an inclined plane. All right, so this is the end of the lesson. I just want to quickly go through this again. We talked about rotational inertia, and we saw that depending on how the mass is distributed around the rotational axis, one object can have a larger rotational inertia compared to the other. In this case, object A, the rod A has a larger rotational inertia. It is harder to start rotating. It is harder to stop rotating. Rod B is easier to start rotating. It is also easier to stop rotating. Therefore, we can say that rod A has more rotational inertia compared to rod B. And we saw the same thing here. If you are spinning something on top of your head, you realize that the longer the rope, the harder it is to start spinning, but also to stop spinning. And therefore, this case shows that there's a larger rotational inertia compared to case one. So larger rotational inertia of the mass. All right, then we looked at a different formula for rotational inertia. For a simple pendulum, rotational inertia is just mr squared. For a solid cylinder, half mr squared. A sphere is 2/5 mr squared. And for a hoop, rotational inertia is I equal to mr squared. And we used that knowledge to deduce that a hoop will always lose the race down an inclined plane. And we said mass doesn't matter. What matters is how the mass is distributed around the rotational axis. Is it away or close to the rotational axis? So that is the factor. How is the mass distributed? That will tell us which one wins the race down an inclined plane. All right, so I will stop here. If you have any questions, please let me know. Bye for now.